Hey there, friend. Today, we're diving into the fascinating world of quantum information and discovering how the tiniest building blocks of reality are already reshaping our computers, our communications, and the way we interact with data. Grab a comfy seat and let's explore this quantum frontier together. Chapter 1. What is quantum information? Quantum information represents a revolutionary departure from classical notions of information, fundamentally reshaping our understanding of computation, communication, and the very nature of reality. Unlike classical information, which is based on bits that can exist in one of two discrete states, quantum information leverages the counterintuitive principles of quantum mechanics, superposition, entanglement, and coherence, to store, transmit, and process data in ways that classical theories cannot accommodate. In this chapter, we will embark on a comprehensive journey through the defining features, practical implementations, theoretical foundations, and future horizons of quantum information, ensuring that you gain a deep and rigorous understanding of this transformative field. To begin with, let us revisit the concept of classical information. In the classical paradigm, the basic building block of information is the bit, which can represent either the state 0 or the state 1. These two distinct states allow for straightforward encoding of data, enabling reliable storage and manipulation in devices ranging from simple flip-flop circuits to advanced digital computers. Classical bits follow deterministic rules. Logical operations such as and, or, and not manipulate bits predictably, and information can be copied and read without fundamentally altering its content. This clarity and reliability underpin decades of technological advancement, from microprocessors to global communication networks. However, classical bits face inherent limitations when tackling certain computational and communication challenges. Problems involving large-scale factorization, complex simulations of quantum systems, and secure long-distance communication often confront exponential scaling barriers. When classical systems attempt to solve these problems, they require computational resources or communication bandwidth that grow uncontrollably with problem size. It is precisely in addressing these barriers that quantum information theory offers unprecedented advantages. Central to quantum information is the concept of the quantum bit, or qubit, which replaces the classical bit. A qubit does not exist solely in one of two states. Instead, it can inhabit a superposition, simultaneously embodying both logical 0 and logical 1 in a coherent combination. This superposed state is characterized by probability amplitudes, which determine the likelihood of collapsing to one of the classical states upon measurement. Because qubits can explore many configurations at once, quantum computers can process vast amounts of information in parallel, theoretically enabling them to outperform classical computers for specific tasks. Superposition alone, however, does not fully capture the power of quantum information. Equally critical is entanglement, a phenomenon in which multiple qubits become linked in such a way that the state of one qubit cannot be described independently of the others, regardless of the distance between them. When two or more particles are entangled, measuring one immediately influences the state of its partners. This instantaneous correlation defies classical intuitions of locality and causality, presenting a unique resource for quantum protocols. Entanglement underlies quantum teleportation, in which the state of a qubit is transmitted from one location to another without physically sending the qubit itself. It also forms the backbone of advanced quantum cryptographic schemes, ensuring absolute detection of any eavesdropping attempt. Maintaining superposition and entanglement in practical systems requires preserving quantum coherence. Coherence refers to the ability of a quantum system to retain its wave-like properties and phase relationships over time. In real-world environments, quantum systems are constantly exposed to noise and interactions that can cause decoherence, an irreversible loss of quantum behavior that effectively reduces qubits to classical bits. Overcoming decoherence demands meticulous isolation of quantum systems, the development of error correction protocols, and engineering innovations in materials and control methods. Contemporary research laboratories around the world devote significant effort to extending coherence times, building fault-tolerant architectures, and integrating error-correcting codes directly into hardware. The practical implementations of quantum information concepts have already begun to emerge. Quantum computing platforms, based on superconducting circuits, trapped ions, photonics, and other physical media, demonstrate small-scale devices capable of executing quantum algorithms. These quantum processors have achieved milestones such as quantum supremacy, wherein a quantum device performs a task that is infeasible for the most powerful classical supercomputers. Although current quantum computers remain noisy and limited in qubit count, rapid progress in hardware development, combined with sophisticated software architectures, promises to scale these devices toward practical, real-world applications. Quantum cryptography offers another compelling application. Quantum key distribution, QKD, protocols utilize the principles of quantum mechanics to exchange encryption keys in a manner that guarantees detection of any eavesdropping attempt. Because measuring a quantum state irreversibly alters it, any third-party interception introduces detectable anomalies, immediately alerting the communicating parties to a security breach. QKD systems are already deployed in specialized networks, protecting sensitive communications in government, finance, and research institutions, and ongoing research aims to integrate quantum-secure communication into conventional network infrastructures. Beyond computing and cryptography, quantum simulation, quantum sensing, and quantum metrology harness quantum information in diverse scientific domains. Quantum simulators employ controllable quantum systems to replicate the behavior of complex quantum phenomena that are intractable for classical computers, such as high-temperature superconductivity, molecular interactions in large biological molecules, and exotic phases of matter. Quantum sensors use entangled states and interference effects to achieve measurement precision beyond classical limits, improving the sensitivity of instruments detecting gravitational waves, magnetic fields, and time intervals. Quantum metrology refines fundamental constants and enables ultra-precise clocks with direct implications for navigation, telecommunications, and fundamental physics experiments. On the theoretical front, quantum information theory extends and refines classical information measures. Quantum entropy concepts, such as von Neumann entropy, generalize Shannon entropy to quantify uncertainty in information content in quantum states. Entropic inequalities and quantum channel capacity theorems explore the limits of information transmission under quantum noise. The study of quantum communication complexity investigates the minimum resources required for distributed quantum tasks, revealing scenarios in which quantum strategies outperform classical ones dramatically. These theoretical insights provide a rigorous foundation for designing next-generation quantum networks and algorithms, ensuring that practical implementations align with fundamental physical limits. Despite the remarkable advances, significant challenges remain in scaling quantum information technologies to widespread deployment. Decoherence, error accumulation, and the precise control of thousands or millions of qubits represent formidable engineering hurdles. The development of fault-tolerant architectures, in which logical qubits are encoded across multiple physical qubits with built-in error correction, is essential. Breakthroughs in cryogenic engineering, photonic interconnects, and novel qubit designs continue to push the frontier. But true fault-tolerant high-volume quantum computers remain an active area of research and development. Interdisciplinary collaboration is vital to surmounting these challenges. Quantum information bridges physics, computer science, electrical engineering, and materials science, demanding integrated approaches to hardware, software, and theoretical frameworks. Universities and research consortia worldwide are expanding curricula and training programs to cultivate a new generation of quantum engineers, theorists, and application developers. Government initiatives and private investments fuel innovation hubs, accelerating translation from laboratory prototypes to commercial systems. Looking ahead, the societal implications of quantum information are profound. Quantum computing could revolutionize drug discovery by simulating molecular interactions with unprecedented accuracy, accelerate optimization in logistics and finance, and unlock new capabilities in artificial intelligence through quantum-enhanced machine learning. Quantum-secure communications promise to safeguard critical infrastructure against emerging cyber threats, while quantum sensors could transform healthcare diagnostics with non-invasive precision measurements. As these technologies mature, industry sectors from energy and transportation to agriculture and climate science may harness quantum tools to address global challenges. In exploring quantum information, we also confront deeper questions about the nature of reality. The quantum informational perspective suggests that information itself, encoded in the superpositions and correlations of quantum states, constitutes a foundational layer of the universe. At the deepest level, particles and fields might emerge from patterns of information processing, blurring the boundary between physical substance and abstract data. This paradigm shift invites reflection on our place within a cosmos where information and physical phenomena are inseparable. In summary, quantum information stands at the intersection of theory and application, bridging abstract mathematical insights with tangible technological breakthroughs. Its study challenges us to rethink long-held assumptions about computation, security, and the fabric of reality. As researchers develop bigger, more reliable quantum systems, industries will confront ethical, societal, and philosophical questions about how to wield unprecedented computational power responsibly. Educational initiatives must evolve, equipping learners with interdisciplinary skills that span quantum physics, computer science, and engineering. Governments and regulatory bodies will need to craft policies to ensure equitable access to quantum technologies while guarding against misuse. At the same time, philosophical and theoretical investigations will delve deeper into whether information is an emergent phenomenon or the substrate from which the universe arises. Every advance in quantum information invites not only new applications, but also fresh questions about the nature of knowledge, agency, and reality itself. In the coming decades, society's embrace of quantum information may mark a turning point as significant as the discovery of electricity or the advent of digital computing, sparking a quantum revolution that reshapes science, technology, and human understanding. As we conclude this chapter, it becomes clear that quantum information is not merely a technological innovation, but a new language for understanding the universe. By mastering the principles and applications of quantum information, we gain the tools to decode nature's most profound secrets and engineer technologies that redefine the possible. Perhaps in the end, our quest to harness quantum information will lead us to a more complete picture of reality, one in which the distinction between matter and information dissolves. Chapter 2. Quantum Computing Explained from Scratch. Quantum computing is a novel paradigm that leverages quantum mechanical phenomena to process information in fundamentally new ways. Unlike classical computing, which relies on bits that exist in definite states of 0 or 1, quantum computing uses quantum bits, or qubits, which can exist in superpositions of states. This feature allows quantum computers to perform certain computations in parallel, potentially achieving speeds and efficiencies far beyond the capabilities of classical machines. To understand this transformative approach fully, we must explore its conceptual foundations, historical development, core components, practical implementations, and broader ecosystem. The conceptual seeds of quantum computing were planted in the early 1980s, when researchers recognized that classical simulations of quantum systems encountered severe scalability challenges. In 1981, a pioneering physicist proposed that a computer built on quantum mechanical principles could efficiently simulate any quantum system, overcoming the exponential resource demands faced by classical simulators. A few years later, the notion of a universal quantum computer emerged, providing a theoretical framework for machines that harness quantum phenomena to perform a wide range of computations. These early ideas established quantum computing as a distinct field at the intersection of physics and computer science. At the heart of quantum computing lies the qubit, the fundamental unit of quantum information. Unlike a classical bit, which firmly resides in one of two states, a qubit can exist in a combination of states simultaneously. When measured, the qubit collapses to one of its definitive states, producing a probabilistic outcome. This probabilistic measurement does not detract from the system's computational utility. Instead, it demands careful algorithm design to amplify correct results and suppress incorrect ones. Qubits derive their unique properties from quantum superposition and interference, enabling a single qubit to encode vastly more information than a classical bit under specific conditions. Quantum logic operations manipulate qubit states through reversible transformations. These operations, commonly referred to as quantum gates, carefully adjust the probabilities and phases of qubit superpositions. Basic transformations can swap the roles of qubit states, create superpositions, or link multiple qubits so that their states become interdependent. A sequence of these transformations forms a quantum circuit, analogous to classical logic circuits, but with the crucial difference that quantum gates preserve information and avoid irreversible energy dissipation. The reversible nature of these gates ensures that the entire computation can, in theory, be reversed, a property that distinguishes quantum processing from classical approaches and underlies the necessity of precise control. A quantum circuit formalizes how quantum gates are applied to a set of qubits in a sequential manner to accomplish a computational objective. Designing effective circuits requires a dual perspective: theoretical insight into algorithmic structure and practical awareness of hardware constraints. The depth of a circuit, or the number of sequential gate operations, influences both computational fidelity and vulnerability to environmental disturbances. Deeper circuits allow for more complex algorithms, but also expose qubits to noise and decoherence for longer durations. Optimizing circuits thus involves balancing algorithmic requirements against the need to minimize error accumulation. Building quantum computers necessitates precise physical implementations of qubits and quantum gates. Several leading platforms have emerged, each with unique strengths. Superconducting circuits use loops of superconducting material formed into tiny islands that can be manipulated by microwave pulses. These systems benefit from established fabrication methods and integration with existing electronics, but require ultra-low temperature environments to maintain superconductivity. Trapped ion platforms hold charged atoms in electromagnetic traps and use laser pulses to drive state transitions. Ion traps offer exceptional coherence times and high-fidelity operations, but face challenges in scaling to large qubit counts. Photonic systems encode qubits in the properties of individual photons, such as polarization or path, enabling room temperature operation and seamless integration with optical communication networks. Other innovative approaches include semiconductor quantum dots, nitrogen vacancy centers in diamond, and topological qubits, each under active research for potential advantages in stability, scalability, or error resilience. Control and readout are vital components of any quantum computing platform. In superconducting systems, carefully shaped microwave pulses target specific qubit circuits to induce transitions between quantum states. Trapped ion systems require finely tuned laser pulses to manipulate electronic and vibrational modes of ions. Once the quantum gates have been applied, measurement protocols convert qubits' quantum states into classical data. High-fidelity readout often involves converting quantum signals into electrical or optical measurements with specialized amplifiers or detectors, ensuring that the measurement accurately reflects the underlying quantum state. Improving readout fidelity remains an ongoing engineering challenge, as measurement errors can propagate through computations and reduce overall accuracy. Quantum systems are inherently sensitive to interactions with their environment, leading to decoherence, the gradual loss of quantum properties such as superposition and entanglement. Decoherence transforms qubits into classical states, erasing the very quantum effects that enable quantum computations. The rate of decoherence depends on factors like ambient temperature, electromagnetic interference, and imperfections in the qubit material. Extending coherence times is essential to perform longer and more complex computations. Strategies to mitigate decoherence include dynamic decoupling techniques, which apply sequences of control pulses to counteract environmental disturbances, and error correction codes that distribute logical quantum information across multiple physical qubits. Quantum advantage refers to the point at which a quantum computer can solve a problem faster or more efficiently than the best-known classical algorithms on classical hardware. Early demonstrations of quantum advantage have focused on narrowly defined tasks, such as sampling from specific probability distributions. While these proofs of concept highlight the potential of quantum machines, achieving practical quantum advantage for real-world applications remains a significant goal. Practical advantages may emerge initially in domains like quantum chemistry, where simulating molecular interactions with high precision can revolutionize materials science and drug discovery. In the current era, often described as the noisy intermediate-scale quantum (NISQ) era, hybrid quantum classical algorithms have gained prominence. These algorithms leverage quantum circuits to evaluate complex quantum states while using classical processors to optimize parameters in real time. Variational approaches and quantum annealing techniques exemplify this strategy, showing promise in optimization problems, machine learning tasks, and simulations of quantum systems. Although NESQ devices face limitations in qubit count and error rates, they provide crucial platforms for testing algorithms, developing error mitigation strategies, and identifying promising application areas for future fault-tolerant quantum computers. Beyond hardware, quantum computing relies on a sophisticated software ecosystem that orchestrates every stage of the computational process. Quantum programming frameworks provide high-level abstractions for building and manipulating quantum circuits, allowing algorithm developers to focus on conceptual design rather than hardware-specific details. Open-source tools such as Qiskit, Cirq, and Forest offer integrated environments for circuit construction, simulation, compilation, and execution on real quantum processors. Cloud-based services hosted by major providers democratize access to quantum hardware, enabling researchers worldwide to experiment with increasingly capable quantum devices and drive innovation collaboratively. Evaluating the performance of quantum computers requires rigorous benchmarking and resource estimation. Quantum volume has emerged as a comprehensive metric that encapsulates several factors, including qubit count, connectivity, gate fidelity, and circuit depth, to provide a single measure of a device's effective computational capability. A higher quantum volume signifies greater potential to execute complex algorithms with minimal errors. Complementary metrics focus on individual gate errors, readout fidelity, and algorithm-specific benchmarks, offering granular insights into hardware strengths and weaknesses. Educational initiatives and workforce development efforts are essential to advance quantum computing. Universities and specialized training programs are rapidly expanding curricula that cover quantum mechanics fundamentals, quantum information theory, and quantum programming. Online courses, workshops, and industry partnerships provide hands-on experience with quantum platforms, preparing students and professionals to contribute effectively to this interdisciplinary field. Collaborations between academic institutions, government agencies, and private enterprises foster research consortia, shared resources, and standardization efforts that accelerate progress towards scalable quantum computing. In conclusion, quantum computing represents a paradigm shift in information processing that integrates deep theoretical principles with cutting-edge engineering. From the foundational concept of qubits and quantum gates to the practical realities of hardware architectures, software stacks, and error mitigation strategies, every facet contributes to the realization of machines capable of surpassing classical limits. As quantum hardware matures, algorithms evolve, and ecosystems expand, quantum computing holds the promise to address challenges in chemistry, optimization, cryptography, and beyond, ushering in a new era of computational capability. Chapter 3: Quantum Algorithms and Their Unmatched Power. Quantum algorithms harness the fundamental features of quantum mechanics to tackle problems that remain intractable for classical computers. At the heart of their power lie quantum resources such as superposition, entanglement, and interference, which allow quantum processes to explore vast solution spaces in parallel, amplify correct answers, and suppress incorrect ones. While classical algorithms follow deterministic or probabilistic rules on bits, quantum algorithms use qubits and quantum operations to exploit wave-like dynamics and non-local correlations. This chapter delves into the foundational concepts, key techniques, landmark algorithms, and emerging frontiers that define the unmatched capabilities of quantum algorithms. The study of algorithms on quantum hardware begins with a re-evaluation of computational complexity. In classical computing, problems are grouped into classes like P for polynomial time-solvable tasks, NP for non-deterministic polynomial verification, and BPP for bounded error probabilistic algorithms. Quantum computation introduces the class BQP, bounded error quantum polynomial time, which captures decision problems solvable efficiently on a quantum computer with high probability of correctness. Understanding the boundaries between BQP, BPP, NP, and other complexity classes is an active area of theoretical research, with implications for cryptography, optimization, and fundamental limits of computation. While it remains unproven whether BQP strictly contains or is contained within other classes, evidence from quantum algorithm development suggests genuine separations for certain structured problems. One of the most critical building blocks for quantum algorithms is the ability to perform transformations that leverage wave interference constructively. Unlike classical processors that execute Boolean logic gates, quantum processors implement reversible operations that manipulate probability amplitudes. Carefully orchestrated sequences of these operations allow amplitudes corresponding to correct solutions to interfere constructively, growing in magnitude, while those corresponding to incorrect answers interfere destructively and diminish. Designing quantum algorithms thus involves crafting circuits that steer amplitude distributions toward desired outputs, a paradigm that stands in contrast to exhaustive search or heuristic sampling in classical methods. A foundational technique behind many quantum algorithms is the quantum version of the Fourier transform. Conceptually, this transformation decomposes a superposed state of qubits into frequency domain components, enabling efficient extraction of periodicity information. Periodicity underpins problems such as factoring and discrete logarithms, which form the basis of modern public key cryptography. By performing a quantum Fourier transform on a carefully prepared input state, a quantum algorithm can identify hidden periods exponentially faster than any known classical algorithm, effectively unraveling number-theoretic structures that remain opaque to classical analysis. Shor's algorithm stands as the most celebrated quantum algorithm, demonstrating that quantum computers can break widely used cryptographic schemes based on factoring large integers. The power of Shor's approach arises from its ability to convert an integer factorization task into a problem of finding the period of a modular exponentiation function. Through quantum superposition and the Fourier transform, Shor's algorithm pinpoints this period in polynomial time. Once the period is known, classical post-processing yields the prime factors. The realization that a sufficiently large and error-corrected quantum computer could render conventional encryption schemes insecure has spurred global efforts to develop both quantum-resistant cryptography and scalable quantum hardware. While Shor's algorithm targets structured algebraic problems, Grover's algorithm addresses unstructured search tasks. Given an unsorted database of n items, a classical algorithm requires O(n) queries in the worst case to find a marked item. Grover's technique instead uses a combination of amplitude inversion and diffusion operations to increase the amplitude of the target state linearly with respect to the number of iterations. After roughly the square root of n iterations, the marked item's amplitude becomes dominant, enabling its retrieval with high probability. Although Grover's speedup is quadratic rather than exponential, it applies broadly to any unstructured search problem, offering a generic quantum advantage across numerous domains such as optimization, cryptanalysis, and machine learning. Many quantum algorithms share a common subroutine known as phase estimation. In phase estimation, a quantum system encodes eigenvalues of a unitary operation into the relative phases of qubit states. By combining controlled unitary evolutions with inverse Fourier-like transforms, quantum circuits can extract these phase values to high precision. Phase estimation is central to algorithms for solving linear systems, estimating Hamiltonian eigenvalues, and implementing quantum simulation protocols. Its versatility makes it a key primitive in the design of advanced quantum routines. Building on the amplitude manipulation paradigm, quantum amplitude amplification generalizes Grover's search mechanism to broader contexts. Instead of simply locating a marked item in a database, amplitude amplification iteratively enhances the probability of states that satisfy a given condition relative to an arbitrary initial state. This technique underlies algorithms for counting solutions, amplitude estimation in Monte Carlo methods, and subroutines in complex quantum simulations, demonstrating how quantum interference can boost success probabilities in algorithmic frameworks beyond searching. Quantum simulation algorithms represent one of the most promising near-term applications of quantum computing. Complex quantum systems in chemistry, physics, and materials science often involve interactions that defy efficient classical modeling due to exponential growth in system size. Quantum simulation leverages qubit registers to directly emulate the underlying quantum dynamics, using techniques such as trotterization and variational methods to approximate time evolution operators. These simulation algorithms hold the potential to reveal novel reaction pathways, design new materials, and explore quantum phases of matter that remain inaccessible to classical computation. The algorithm for solving large systems of linear equations, often known by its initials HHL, extends phase estimation to linear algebra tasks. By encoding a vector into a quantum state, applying controlled unitary operations that reflect matrix properties, and performing conditional rotations, this algorithm can output a quantum state proportional to the solution vector. Although extracting full classical solutions may require additional processing, the algorithm's promise lies in applications where one needs to estimate aggregate properties of the solution, such as expectation values, offering exponential speedups under favorable conditions. Quantum walks offer another rich algorithmic framework, drawing analogies to classical random walks but exploiting quantum interference to speed up traversal on graphs. Quantum walk algorithms can solve element distinctness problems, evaluate Boolean formulas, and facilitate spatial search with proven speedups. The flexibility of quantum walks extends to algorithmic design for sampling and quantum transport processes, illustrating how quantum dynamics on structured networks can outperform classical counterparts. Adiabatic quantum computing and quantum annealing take an alternative approach to algorithm design. Rather than applying discrete gates, these paradigms gradually transform an initial Hamiltonian, whose ground state is easy to prepare, into a final Hamiltonian that encodes the problem of interest. If the evolution proceeds slowly enough, the adiabatic theorem ensures the system remains in its ground state, culminating in the solution. Quantum annealing hardware, tailored to optimization tasks, implements this idea in analog form, focusing on energy landscapes to locate global minima. While formal guarantees of speedup are still under investigation, empirical results demonstrate promising performance on certain combinatorial problems. Hybrid quantum classical algorithms merge quantum subroutines with classical optimization loops. Variational methods, such as the variational quantum eigensolver and the quantum approximate optimization algorithm, use parameterized quantum circuits to prepare trial states. Classical optimizers iteratively adjust these parameters to minimize or maximize objective functions. Hybrid schemes reduce circuit depth requirements, making them suitable for current noisy quantum devices. These algorithms have shown early successes in finding ground states of small molecules and solving simple optimization problems, marking an important transitional phase toward fault-tolerant implementations. Quantum sampling algorithms, including boson sampling, demonstrate how sampling from certain quantum-generated probability distributions can be computationally intensive for classical machines. Boson sampling exploits the behavior of indistinguishable photons passing through linear optical networks to produce output patterns with distribution complexity believed to lie beyond classical reach. Although boson sampling systems are not universal quantum computers, they offer evidence of quantum computational supremacy, showcasing tasks where quantum processes outpace classical simulation. Each quantum algorithm requires careful consideration of resource costs, including qubit counts, gate fidelities, circuit depths, and coherence times. The ultimate feasibility of an algorithm depends on matching its resource demands with hardware capabilities. Benchmarking efforts quantify performance by simulating idealized algorithms on near-term devices and extrapolating resource requirements for fault-tolerant scales. Such studies guide research priorities, identifying algorithms that strike the best balance between quantum advantage and practical implementability. Despite these advances, quantum algorithms face significant challenges: error accumulation, hardware connectivity restrictions, and the need for large numbers of high-quality qubits pose obstacles. Efficient error correction protocols inflate resource requirements, while maintaining low-error gate operations demands precise control. Circuit compilation techniques and algorithmic optimizations continue to evolve, seeking to minimize overheads and fit algorithms within the constraints of emerging hardware. Looking forward, the future of quantum algorithms lies in exploring new problem domains, refining algorithmic primitives, and uncovering deeper complexity theoretic insights. Areas such as quantum machine learning, quantum optimization, and quantum-enhanced data analysis stand poised to benefit from bespoke algorithms that leverage specialized quantum resources. Researchers are also investigating algorithmic frameworks for quantum networked systems, distributed quantum computing, and quantum cryptographic protocols that integrate computational and communication tasks. In sum, quantum algorithms represent a radical departure from classical approaches, reshaping our understanding of what is computationally possible. By exploiting superposition, entanglement, and interference, these algorithms navigate solution spaces with unparalleled efficiency. Landmark breakthroughs like Shor's and Grover's algorithms illustrate the potential for exponential and quadratic speedups. As new algorithmic techniques emerge and hardware matures, quantum algorithms will continue to expand the horizon of computational capabilities, driving innovation across science, engineering, and beyond. Chapter 4: Quantum Cryptography: How Quantum Mechanics Secures Information. Quantum cryptography applies the laws of quantum physics to protect communication in ways that classical cryptography cannot replicate. By leveraging phenomena that have no analog in ordinary digital systems, quantum cryptography offers security grounded in the very fabric of reality, rather than assumptions about computational difficulty. This chapter explores the origins, fundamental principles, practical implementations, theoretical proofs, and future prospects of quantum cryptography, providing a thorough account of how quantum mechanics can guarantee the confidentiality and integrity of information against both present and future threats. At the heart of quantum cryptography lies the insight that measuring a quantum system inevitably disturbs it. Unlike classical signals that can be copied and read without alteration, quantum states cannot be observed passively. Any attempt at interception introduces detectable anomalies. This measurement disturbance forms the foundation of protocols that detect eavesdropping immediately, ensuring that any adversary attempting to gain information alters the quantum signals and reveals their presence. The inability to clone unknown quantum states, formalized as the no-cloning principle, further prevents an attacker from making perfect copies of quantum information for later analysis. The first practical quantum key distribution system was developed to demonstrate these principles. In this method, a sender encodes bits in the quantum states of particles, transmitting them over a channel to a receiver. By randomly choosing between two sets of non-orthogonal quantum states, the sender ensures that any measurement by an eavesdropper introduces a certain error rate. After transmission, legitimate parties compare portions of their data over a public channel to estimate the error rate. If the error rate remains below a theoretical threshold, they proceed to distill a shared secret key using classical post-processing techniques, including error correction and privacy amplification, to remove any partial information an adversary may have gained. This approach secures the resulting key with information theoretic guarantees, meaning that security holds even against adversaries with unlimited computing power. Building upon the original schemes, entanglement-based quantum key distribution protocols employ pairs of quantum particles generated in linked states. These particles remain correlated no matter how far they separate. When one party measures a particle, the outcome of that measurement instantaneously reflects in the partner particle held by the other party. By measuring many such pairs, both parties generate correlated strings of bits. Any eavesdropping attempt disrupts these delicate correlations, producing statistical deviations that reveal unauthorized intervention. Entanglement-based methods simplify certain security proofs and enable device-independent approaches, where security follows directly from the observed correlations rather than trusting the internal workings of the hardware. Beyond discrete quantum states, continuous variable quantum cryptography uses properties such as the amplitude and phase of light waves. In this approach, information is encoded in continuous observables rather than distinct polarization states. Coherent and squeezed light sources generate states that legitimate receivers measure using homodyne or heterodyne detection techniques. Continuous variable systems often benefit from compatibility with existing optical communication infrastructure, as they can use standard components like lasers and photodiodes. Their security proofs rely on analogous principles. Measurement disturbance and uncertainty relations guard against eavesdropping, while classical post-processing secures the final key. Practical implementations of quantum cryptography span fiber optic networks, free space links, and satellite platforms. In metropolitan fiber networks, quantum signals travel through dedicated optical fibers alongside classical data channels. Researchers have demonstrated key distribution over tens to hundreds of kilometers of fiber, integrating quantum channels with existing telecom infrastructure. Free space implementations use telescopes to transmit and receive quantum states in open air, enabling secure links between buildings, across bodies of water, or even from ground stations to airborne platforms. Satellite-based experiments extend quantum cryptography to global scales, bridging continents by exchanging quantum signals between orbiting satellites and ground receivers, overcoming the distance limitations of terrestrial channels. Theoretical security proofs underpinning quantum cryptography have evolved significantly. Early proofs considered idealized hardware and gave bounds on tolerable error rates. Rigorous frameworks now treat cryptographic tasks as composable primitives, ensuring that quantum key distribution systems remain secure even when integrated into larger communication protocols. These proofs account for imperfections in sources, detectors, and channels, deriving conservative bounds that guarantee security under the worst-case scenarios. By combining finite key analysis, decoy state methods to detect photon number attacks, and device-independent proofs based on entanglement tests, modern quantum cryptography achieves robust defenses against sophisticated adversaries. Device security, however, depends not only on fundamental physics, but also on careful engineering to prevent loopholes. Side-channel vulnerabilities, such as timing information, detector efficiency mismatches, and imperfect state preparation, can leak information to attackers. Countermeasures include randomizing detector parameters, implementing measurement device-independent protocols that remove trust requirements from detectors, and using hardware calibration procedures that certify device performance. Laboratories and companies developing quantum cryptography systems conduct extensive testing to close side channels, employing techniques like randomized testing, error monitoring, and tamper-evident packaging. Quantum cryptography integrates into emerging quantum networks, where nodes exchange keys and entangled particles to establish secure links. Quantum repeaters extend the reach of quantum signals by performing entanglement swapping and purification in intermediate stations, enabling long-distance transmission without direct loss of fragile quantum states. These repeater nodes store quantum information in memory elements, synchronize operations across the network, and correct errors introduced by noise and loss. Building a scalable quantum network requires advances in quantum memory fidelity, quantum error correction, and reliable entanglement distribution protocols that can tolerate realistic imperfections. Standardization and industry initiatives aim to commercialize quantum cryptography for real-world deployment. Standards bodies define system requirements, interface protocols, and security certification procedures. Companies offer turnkey systems for governments, financial institutions, and critical infrastructure operators, integrating quantum key distribution hardware with classical network management tools. Pilot projects test interoperability between vendors, assess performance in live environments, and evaluate lifecycle management, from initial deployment through maintenance and eventual upgrades. Hybrid cryptographic architectures combine quantum key distribution with classical encryption schemes to balance performance and security. In such systems, quantum-generated keys seed classical symmetric ciphers that encrypt bulk data at high speeds. This hybrid approach leverages the long-term security guarantees of quantum cryptography for key exchange, while relying on efficient classical ciphers for data encryption, delivering end-to-end security with manageable resource requirements. Emerging protocols extend quantum cryptography beyond key distribution, encompassing quantum digital signatures, quantum secret sharing, and quantum secure direct communication. Quantum digital signatures encode authenticity information in quantum states, enabling recipients to verify the source and integrity of messages without trusting classical signature schemes. Quantum secret sharing divides a secret into quantum fragments distributed among multiple parties, ensuring that only authorized subsets can reconstruct the original data. Quantum secure direct communication transmits information directly through quantum channels, embedding both message and authentication in quantum states and eliminating the need for separate encryption stages. Quantum random number generators complement cryptographic protocols by producing high-quality randomness harnessed from inherent quantum unpredictability. Unlike classical pseudo-random generators, quantum processes yield true randomness through measurement of superposed or entangled states. These devices underpin secure key generation, stochastic simulations, and cryptographic applications requiring unpredictable seeds. International collaborations drive protocol standardization and large-scale testbeds for quantum cryptography. Research consortia and government initiatives coordinate multidisciplinary efforts to build interoperable networks, develop certification standards, and integrate quantum-safe solutions with classical infrastructure. Pilot deployments in finance, healthcare, and government communications demonstrate practical utility and inform best practices for future rollouts. Challenges in scaling quantum cryptography to widespread adoption include manufacturing costs, integration complexity, and regulatory frameworks. Building quantum-grade hardware demands specialized components such as single-photon sources, low-noise detectors, precision timing electronics, and robust quantum memories. Optimizing system cost and form factor for network operators remains critical. Moreover, governments and regulatory bodies must establish guidelines for approved quantum cryptography systems, coordinating international standards to ensure global interoperability and compliance with data protection laws. Future research directions include novel protocols that further reduce vulnerability to side channels, improved quantum repeaters enabling universal quantum network architectures, and integration with post-quantum classical algorithms to provide multi-layered security. Advances in photonic integration may yield chip-scale quantum cryptography devices embedded directly into standard network equipment. As scalable, fault-tolerant quantum computers approach practical realization, the urgency to deploy quantum-safe communication infrastructures escalates, making quantum cryptography a vital component of future cybersecurity landscapes. In the coming decades, quantum cryptography will transform how societies protect their most sensitive information. By anchoring security in the immutable laws of physics rather than computational assumptions, quantum cryptography offers a path to truly unbreakable encryption. As research and development advance, the vision of a global quantum internet, where information flows seamlessly and securely via quantum channels, moves ever closer to reality, reshaping privacy, commerce, and national security in the quantum age. Chapter 5. Quantum Error Correction: Protecting Fragile Quantum Data. Quantum computers promise unprecedented computational power, yet this promise hinges on maintaining the delicate quantum states of qubits in the face of relentless disturbances. Unlike classical bits, which can be reliably copied and restored when errors occur, quantum information cannot be duplicated or simply refreshed due to fundamental quantum constraints. On top of that, Quantum systems are inherently susceptible to decoherence and noise arising from interactions with their environments. Quantum error correction thus emerges as an essential pillar for building large-scale, reliable quantum machines, safeguarding fragile quantum data and enabling the realization of fault-tolerant quantum computation. In developing quantum error correction methods, researchers confronted two profound challenges stemming from the very nature of quantum information. First, the no-cloning theorem forbids the creation of identical copies of an arbitrary quantum state, eliminating the straightforward strategy of duplicating data for redundancy. Second, quantum measurements generally destroy the superpositions and entanglements that encode information, preventing direct inspection of qubit states. Overcoming these hurdles required inventing novel schemes that protect quantum information indirectly by spreading logical information across multiple physical qubits and using carefully designed measurements that reveal error syndromes without collapsing encoded data. At the heart of quantum error correction lies the concept of the logical qubit. Instead of representing one qubit with a single physical system, error correction encodes the logical qubit's state across an ensemble of physical qubits. By doing so, any single qubit error can be detected and corrected by examining the relationships among the physical qubits without directly observing the logical state. Syndrome measurements extract information about which errors have occurred, while preserving the coherent superposition that carries computation. This delicate procedure protects the encoded information against noise processes such as bit flips, phase flips, and more general decoherence channels. One of the earliest breakthroughs in quantum error correction was the discovery of a method that encodes one logical qubit into 3 physical qubits, allowing detection and correction of a single type of error. Building on those insights, researchers developed more robust codes capable of handling multiple error types simultaneously by using larger blocks of qubits. These codes demonstrated that it is theoretically possible to correct arbitrary single-qubit errors if enough redundancy and properly structured measurements are used. The realization that quantum information could be protected against noise in principle laid the groundwork for fault-tolerant computation. As research progressed, more efficient and scalable error-correcting codes were introduced. Stabilizer codes provided a powerful algebraic framework to describe error correction systematically. Within this framework, quantum codes are defined by a set of operators whose joint eigenstates represent valid code words. Errors manifest as deviations from these eigenvalues, and syndrome measurements detect which stabilizer constraints have been violated. The formalism unified many earlier codes, allowing systematic exploration of code families with desirable properties, such as high error thresholds and low overhead. Among the most prominent stabilizer codes is the surface code, which arranges qubits on a 2-dimensional grid with nearest neighbor interactions. Surface codes exploit local measurements of qubit neighborhoods to identify and correct errors efficiently, making them highly compatible with hardware architectures that naturally support planar qubit layouts. Crucially, the surface code boasts one of the highest known error thresholds. If the physical error rate per qubit and gate falls below a certain threshold, logical errors can be suppressed arbitrarily by increasing the code's size. This threshold theorem guarantees that sufficiently large, low-error hardware can perform fault-tolerant computation indefinitely. Implementing quantum error correction in practice demands integrating active syndrome measurements, classical control logic, and feedback operations within the quantum processing cycle. During computation, ancillary qubits interact with data qubits to extract error information, then are measured to produce binary syndrome results. These results feed into real-time classical processors that identify the most likely error chains and instruct quantum hardware to apply the appropriate corrections. Achieving low latency, high-fidelity operations for all components is vital, as delays or measurement errors can propagate faults and undermine the correction process. Experimental demonstrations of error correction represent a major milestone. Researchers have shown the ability to prepare encoded states, detect errors, and apply corrective operations on small logical qubits in superconducting circuits and trapped ion systems. These experiments validate the underlying theory by preserving quantum coherence for longer durations than unprotected qubits. Though these early implementations involve modest code sizes and limited error suppression, they serve as critical stepping stones toward scalable, fault-tolerant quantum processors that can reliably execute complex algorithms. Scaling up quantum error correction introduces significant challenges. Large-scale codes require thousands or millions of physical qubits to encode a meaningful number of logical qubits with sufficiently low error rates. Qubit connectivity, measurement fidelity, and classical processing speed all become central concerns. Efficient qubit routing, error decoding algorithms, and minimizing qubit idle times are active research areas. Hardware designers explore modular architectures that enable parallel error correction across code patches, while software teams develop optimized decoders that rapidly translate syndrome data into correction instructions, even in the presence of measurement noise. Real-world quantum applications shape the requirements for error-corrected systems. For quantum simulation tasks, tolerating modest logical error rates may suffice, while cryptographic or financial optimization applications could demand near-zero logical error rates for secure performance. Tailoring code parameters, such as code distance and qubit overhead, to match the performance needs and hardware capabilities of specific applications is essential to optimize resource usage and computational throughput. Comprehensive analyses reveal trade-offs between physical qubit quality, code overhead, and expected performance. High-fidelity qubits and gates reduce the required code size for a given logical error rate, while faster measurements and feedback shorten the correction cycle. As hardware improves, designers can reduce redundancy and repurpose qubit resources for logical operations. Multi-level concatenated codes, combining several layers of error correction, offer alternative approaches for achieving extreme reliability, but often at the cost of increased complexity. Beyond active error correction, passive protection methods contribute to stable quantum memory. Topological codes inherently store information in non-local properties of a system, making them robust against local perturbations. While active syndrome-based approaches require continuous intervention, passive stabilization leverages system Hamiltonians engineered so that logical information corresponds to ground state properties separated by an energy gap from excitations. Research into combining passive and active strategies may yield hybrid schemes that balance overhead and stability. Looking forward, integrating error correction with quantum algorithms remains a dynamic frontier. Fault-tolerant gate constructions enable logical qubit manipulation without leaving the protected code space, using specialized sequences of operations that commute with stabilizer measurements. Resource-efficient implementations of common quantum gates, such as magic state injection and distillation, are under intense investigation as they represent some of the most resource-hungry aspects of fault-tolerant architectures. Developing optimized fault-tolerant protocols for specific algorithmic tasks could substantially reduce overall overhead. Advances in material science and device engineering also promise to boost error correction performance. Qubit designs with lower intrinsic noise rates, improved control electronics, and novel error-transparent operations can suppress dominant error channels. Integrated cryogenic control systems and high-bandwidth cryogenic electronics may enable ultra-fast syndrome extraction and correction. Collaboration between hardware, software, and theoretical communities is crucial to co-design systems that meet error correction requirements from the ground up. Education and training for quantum error correction emerge as essential components of preparing a skilled workforce. Universities and research centers develop specialized courses and workshops on quantum error correction theory, code implementation, and syndrome decoding. Open-source platforms provide simulation tools and demonstration modules that allow students and engineers to experiment with codes, test decoders, and analyze performance under realistic noise models, fostering widespread adoption of robust error correction practices. Eventually, error-corrected quantum computers will unlock the full potential of quantum algorithms, reliably solving problems in chemistry, optimization, cryptography, and beyond, tasks that unprotected devices cannot tackle due to noise limitations. The journey from noisy intermediate-scale machines to fault-tolerant quantum processors hinges on mastering the art and science of error correction, transforming vulnerability into resilience. As we refine these techniques, quantum error correction not only safeguards quantum data, but also illuminates deeper connections between information theory, physics, and computation. By understanding and mitigating errors at a fundamental level, we gain insights into the interplay between noise, redundancy, and coherence, revealing principles that may inform new approaches to computation and communication in the quantum era. In protecting fragile quantum data, we safeguard both our technological aspirations and our pursuit of knowledge at nature's most fundamental level. Chapter 6: Quantum Simulations Modeling the Unmodelable. Quantum simulation has emerged as a revolutionary approach to explore the behavior of quantum systems that cannot be captured by classical computation due to extreme complexity. By harnessing the fundamental principles of quantum mechanics directly, researchers can emulate interactions and dynamics in a controlled laboratory environment, transforming abstract theoretical models into tangible experiments. This field responds to Richard Feynman's insight that quantum systems resist efficient classical simulation, offering instead the possibility of building one quantum system to study another. Through a combination of digital gate operations, engineered analog interactions, and hybrid schemes, quantum simulation accelerates our understanding of phenomena ranging from molecular bonds to the exotic phases of matter and fundamental forces governing the universe. In the digital implementation of quantum simulation, the central challenge is to translate continuous time evolution into a discrete sequence of elementary operations without overwhelming the device with excessive depth. Early methods introduced a systematic partitioning of time into small intervals, approximating the continuous evolution of complex interactions by iterative application of simple transformations. Over time, more refined approaches have emerged, employing adaptive techniques that adjust both the duration and nature of these intervals in response to real-time measurements of fidelity. Compiler tools optimize the mapping of abstract models onto specific hardware architectures, taking into account qubit connectivity and gate repertoire. These compiler optimizations perform advanced scheduling that minimizes idle time for qubits, further reducing cumulative noise. As error-corrected quantum processors become available, digital simulation frameworks will transition seamlessly to fault-tolerant regimes, where logical qubits maintain coherence over the long execution of deep circuits. Analog simulation complements digital methods by exploiting the natural interactions within a physical platform. Systems of ultra-cold atoms arranged in optical lattices use standing waves of laser light to create periodic potentials where atoms mimic the behavior of electrons in crystals. By tuning laser intensities and magnetic field gradients, experimentalists can reproduce a wide spectrum of condensed matter models. The trapped ion approach leverages high-precision laser pulses to couple ions' internal states with collective vibrational modes, effectively generating spin models with tunable range and disorder. Photonic simulators use the interference of light in coupled waveguides and cavities to emulate bosonic phenomena, facilitating the study of quantum networks and open system dynamics. These analog approaches benefit from direct mapping, high coherence, and the ability to observe time-dependent responses of many-body systems, illuminating processes such as quantum phase transitions and critical scaling. More recently, hybrid paradigms have risen to prominence by intertwining analog evolution with digital flexibility. In variational simulation algorithms, a parameterized quantum circuit prepares trial states that approximate the target system's low-energy configurations. Classical processors evaluate measured observables and iteratively adjust circuit parameters, converging toward optimal representations of ground and excited states. This interplay allows researchers to skirt the limitations of noisy devices by restricting circuit depth while retaining the ability to explore complex Hamiltonians. Advances in ansatz design incorporate problem-specific structures that capture essential correlations with minimal overhead. By iteratively refining both quantum and classical components, hybrid methods bridge the gap between current hardware capabilities and the demands of scientifically relevant simulations. The impact of quantum simulations in chemistry is already tangible. Small molecules have been studied with unprecedented precision, validating approaches that calculate electronic structure, reaction pathways, and energy barriers. In silico experiments reveal how catalysts facilitate bond rearrangements, guiding the design of more efficient materials for energy conversion and storage. Simulations of photochemical processes shed light on light harvesting mechanisms in natural and synthetic systems, laying the groundwork for next-generation solar technologies. As qubit counts and coherence times increase, quantum simulations will extend to complex biomolecular interactions, informing drug discovery by predicting binding affinities and reaction kinetics that elude classical approximations. Condensed matter physics stands to benefit profoundly from quantum simulation. Investigations into high-temperature superconductivity probe models of interacting electrons on lattices, exploring how subtle variations in interaction strengths give rise to superconducting phases. Quantum simulators enable direct observation of vortices, pairing mechanisms, and the interplay between magnetism and electron motion. Studies of spin liquids, systems characterized by frustrated interactions and emergent excitations, reveal topological orders and anionic behaviors that defy conventional classification. By emulating disorder-driven localization and many-body localization, simulators clarify how isolated quantum systems depart from classical expectations, offering insights into thermalization and ergodicity in complex materials. High-energy physics applications take quantum simulation into the realm of gauge theories and particle interactions. Models of quark confinement and asymptotic freedom are investigated through discretized gauge fields implemented in cold atom lattices and superconducting circuits. Simulators reproduce string breaking and hadronization processes under extreme conditions, offering glimpses into the early universe's primordial plasma. Extending these techniques to higher dimensions and non-abelian gauge groups promises to unravel the behavior of matter under extreme fields, inaccessible to traditional experimental facilities. Quantum simulators thus become complementary tools to particle accelerators, opening a new window into the fundamental forces binding the cosmos. In biological contexts, quantum simulation begins to explore whether quantum effects play non-trivial roles in life's processes. Coherence in photosynthetic complexes, proton tunneling in enzymes, and electron transfer in respiratory chains are subjects of active investigation. Hybrid analog-digital protocols map vibronic interactions and environmental couplings, uncovering potential quantum contributions to biological efficiency. While classical models capture many biochemical processes, quantum simulators may reveal mechanisms that enhance reaction rates, or regulate energy flow in living systems, inspiring biomimetic technologies for sensing and catalysis. Across these domains, error mitigation strategies are pivotal for extracting reliable data from imperfect devices. Techniques such as extrapolating measurements taken at varied noise levels to approximate ideal results, probabilistic cancellation of noise operators informed by detailed calibration, and randomization schemes that convert coherent errors into stochastic ones empower researchers to push current hardware beyond its raw error rates. Benchmarking protocols leverage known symmetries and conservation laws of target models to validate simulation accuracy. These mitigation methods bridge the gap until full error correction becomes feasible, enhancing the utility of near-term quantum simulators. Software frameworks weave together model specification, noise-aware compilation, and execution orchestration. High-level interfaces allow scientists to describe Hamiltonians in their native theoretical language, automatically translating these descriptions into hardware-specific control sequences or gate arrays. Real-time feedback from hardware diagnostics informs dynamic adjustments, optimizing pulse shapes and gate timings on the fly. Cloud-based platforms democratize access, offering unified workflows that manage qubit reservations, data collection, and post-processing. Integration with classical high-performance computing enables distributed simulations where quantum processors handle the intrinsically quantum parts, while classical resources manage data analysis and parameter optimization. Scaling quantum simulations to fault-tolerant regimes poses ambitious engineering demands. Encoding large-scale simulations into logical qubits protected by error correction codes requires significant overhead. Optimizing resource allocation involves balancing code distance with qubit quality and architectural constraints. Novel error-corrected analog simulators, where system Hamiltonians include built-in protection against common noise channels, are under exploration to reduce overhead. As hardware platforms evolve toward modular, networked architectures, distributed quantum simulation emerges as a concept where clusters of quantum nodes collaborate on large problems, mirroring classical supercomputing clusters but with quantum interconnects for entanglement distribution. Beyond technical achievements, quantum simulation fosters a paradigm shift in scientific methodology. By unifying computation and experiment within a quantum framework, researchers engage in iterative cycles of hypothesis generation, simulation, and experimental validation on the same platform. This convergence accelerates discovery, enabling rapid prototyping of theoretical models and direct observation of emergent phenomena in situ. As quantum digital twins, virtual replicas continuously updated with real-time data, become feasible, scientists will gain unprecedented predictive power over complex quantum and classical systems, spanning materials design, chemical processes, and beyond. Modeling the unmodelable, quantum simulation transcends traditional computational barriers, offering a new lens through which to view nature's most intricate dynamics. As hardware and software co-evolve, quantum simulators will unlock mysteries from subatomic particles to living cells, reshaping our approach to research and innovation. By embodying theoretical constructs within experimental realities, quantum simulation stands at the frontier of human understanding, charting a course toward a future where the boundaries between thought and experiment, simulation and reality dissolve in the quantum tapestry of discovery. Chapter 7. Quantum Networking, the Coming Quantum Internet. Quantum networking represents the next frontier in information technology, promising to interconnect quantum processors, sensors, and communication nodes through entangled links. Unlike the classical internet, which transmits bits through optical fibers, wireless signals, and electronic routers, a quantum network must distribute qubits and entanglement across diverse media while preserving fragile quantum states. The quantum internet concept envisions a global fabric of interconnected quantum nodes that can exchange quantum information directly, perform distributed quantum computing tasks, and enable applications beyond the reach of classical networks. Building this infrastructure requires reimagining network architectures, control protocols, and hardware components to operate in the quantum regime, where measurement-induced collapse and environmental noise pose fundamental obstacles. At the heart of quantum networking lies entanglement distribution, serving as the currency for quantum communication. Entangled qubit pairs act as links between distant nodes, enabling teleportation of unknown quantum states without physically transmitting qubit carriers. Quantum teleportation exploits these shared entangled resources and classical communication to transfer quantum information securely and losslessly in principle. Achieving large-scale teleportation demands not only high-fidelity entanglement generation, but also precise synchronization of measurement outcomes and adaptive feed-forward operations at receiving nodes. Orchestrating these complex sequences across network distances underpins the design of quantum protocols that go beyond simple point-to-point connections, laying the groundwork for multi-node quantum communication. Quantum repeaters emerge as critical components in overcoming loss and decoherence that plague long-distance entanglement distribution. Optical fibers and free space channels suffer from exponential attenuation, limiting direct entanglement distribution to tens of kilometers. Quantum repeaters segment the total distance into shorter links, where entanglement is first established locally. Through entanglement swapping and purification steps at intermediate nodes, longer distance entanglement is gradually extended while correcting for noise. Implementing repeaters requires quantum memories to store entangled states until adjacent links are ready, along with local quantum processing to perform the necessary Bell state measurements and error management. The performance of a repeater chain hinges on memory coherence times, gate fidelities, and the efficiency of heralding signals that indicate successful entanglement. Entanglement swapping protocols interconnect segmented links by performing joint measurements on qubits stored in quantum memories at a repeater node. When a successful measurement occurs, it projects remote qubits into an entangled state, effectively linking distant network segments. To ensure the overall fidelity remains above usable thresholds, purification routines exploit redundancy and probabilistic processes to detect and discard low-quality entangled pairs. Balancing the trade-off between entanglement generation rate and purification overhead is central to repeater network design, influencing metrics such as throughput, latency, and resource consumption. Researchers constantly refine these protocols to optimize performance under realistic noise models and hardware constraints. Quantum memories form the backbone of repeaters by storing quantum states with minimal degradation over relevant timescales. Physical implementations range from trapped atomic ensembles and defect centers in solid-state materials to superconducting circuits coupled to microwave resonators. Each platform offers unique advantages in coherence times, bandwidth, and integration with optical interfaces. Engineering memories that support multimode storage and on-demand retrieval is crucial for flexible network architectures, allowing simultaneous entanglement attempts across different channels and adaptive scheduling to maximize throughput. Memory operations must integrate seamlessly with entanglement generation hardware and classical control electronics, requiring tight synchronization and efficient error detection mechanisms. Beyond simple linear repeater chains, network architectures must support routing, switching, and multiplexing of quantum information across a mesh of interconnected nodes. Network protocols must manage entanglement resources dynamically, selecting paths that optimize success probability while minimizing delay. Quantum routing algorithms involve decision-making under uncertainty as entanglement generation is probabilistic and link failures can necessitate real-time reconfiguration. Network control planes integrate quantum-specific signals, such as heralding notifications for successful entanglement generation, with classical communication channels, enabling distributed coordination reminiscent of classical internet routing, but augmented by quantum state management and resource tracking. Hardware integration poses a formidable challenge in building a quantum internet. Quantum nodes must interface with both quantum and classical hardware layers, supporting quantum state generation, manipulation, memory, and measurement alongside classical processors for protocol control and error correction. Photonic interfaces convert between flying qubits in optical fibers and stationary qubits in memory modules, while microwave to optical transduction schemes aim to bridge disparate technological domains. The development of on-chip integrated photonics, cryogenic control electronics, and compact cryostats promises to reduce footprint and power consumption, bringing quantum networking hardware closer to deployable form factors. Satellite-based quantum links complement terrestrial fiber networks by enabling entanglement distribution across thousands of kilometers with minimal atmospheric loss. Low Earth orbit satellites equipped with entanglement sources and quantum transceivers can beam entangled photons down to multiple ground stations, establishing secure links over continental scales. Successful experiments have demonstrated satellite-to-ground entanglement and quantum key distribution, proving the feasibility of a space-based layer in the quantum internet. Integrating satellite networks with fiber and free space segments creates a heterogeneous global infrastructure, where optimal routes may involve combinations of ground and orbital links based on availability, weather conditions, and required security levels. Quantum network protocols layer above the physical hardware to define standards for encoding, transmitting, and processing quantum information. The development of a protocol stack for the quantum internet parallels the classical OSI model with distinct abstraction levels for physical connectivity, link management, network routing, and application services. Quantum-specific layers handle entanglement routing, resource reservation, and adaptive error management, while higher layers support secure quantum communication, distributed computation tasks, and networked quantum sensing. Establishing interoperable standards is essential to ensure compatibility between hardware vendors and national research infrastructures, driving coordinated efforts in standard development organizations. Applications of quantum networking extend far beyond secure key distribution. Distributed quantum computing harnesses networked quantum processors to tackle computational tasks that require more qubits than a single device can provide. By sharing entanglement and teleporting qubits between processors, a geographically distributed quantum computer can multiply its effective computational capacity. Achieving this vision requires low latency, high-fidelity quantum channels and synchronized control protocols that coordinate multi-node gate operations across network links. Quantum clock synchronization exploits entanglement correlations to align time standards with precision unmatched by classical methods. By sharing entangled pairs and performing correlated measurements, distant clocks can be synchronized to fluctuations at sub-nanosecond or even picosecond scales, enhancing navigation systems, radio astronomy arrays, and fundamental tests of relativity. Quantum sensor networks leverage distributed entanglement to correlate measurements across spatially separated nodes, improving sensitivity for applications such as gravitational wave detection, geomagnetic field mapping, and environmental monitoring. Beyond pure quantum tasks, hybrid networks integrating quantum and classical resources offer incremental benefits in the near term. Quantum channels can augment classical cybersecurity by distributing one-time pads that are provably secure, while classical infrastructure handles bulk data transport. Hybrid network management systems coordinate quantum entanglement generation with classical routing and encryption, offering layered security solutions that evolve as quantum hardware matures. These hybrid approaches smooth the transition from conventional networks to full-scale quantum internets. Theoretical and experimental research communities are forging international collaborations to build testbeds and pilot networks that demonstrate end-to-end quantum communication and distributed quantum services. Consortia pool resources to deploy multi-node platforms across urban centers, interconnecting universities and research labs. These testbeds serve as crucibles for protocol validation, hardware benchmarking, and development of network management tools. Lessons learned from these early networks inform scalability strategies, error budgets, and performance targets for future commercial deployments. Challenges to realizing a global quantum internet remain substantial. Overcoming photon loss in optical channels, improving memory lifetimes, scaling up repeater node density, and ensuring secure integration with classical infrastructure all demand coordinated advances across physics, engineering, computer science, and policy. Security frameworks must evolve to address quantum-specific threats and trust models, balancing the openness of network access with safeguards against malicious actors. Regulatory and legal considerations will shape spectrum allocation, cross-border data flows, and certification of quantum communication systems. Nevertheless, the vision of a quantum internet capable of linking quantum devices worldwide is steadily coming into focus. Continued progress in entanglement distribution, quantum memory engineering, and network control software heralds a future where quantum networking becomes as ubiquitous as today's classical internet. This emerging infrastructure promises to unlock new modes of scientific collaboration, secure communication, and computational power. In building the coming quantum internet, researchers and engineers stand at the threshold of transforming how people, devices, and data connect in the quantum age. Chapter 8: Quantum Machine Learning: Leveraging Quantum Power in AI. Quantum machine learning explores how quantum processors can accelerate, enhance, or fundamentally transform tasks traditionally handled by artificial intelligence. As classical machine learning scales to handle ever larger datasets and more complex models, computational bottlenecks emerge, especially in high-dimensional optimization, kernel evaluations, and generative modeling. Quantum machine learning seeks to harness quantum parallelism, high-dimensional feature spaces, and novel data encoding schemes to address these challenges, offering potential advantages in both training efficiency and model expressiveness. A central motivation for quantum machine learning arises from the ability of quantum systems to represent information in exponentially large state spaces. While classical neural networks operate on vectors of real numbers and learn mappings through layer-wise transformations, quantum circuits manipulate amplitude distributions over bit strings, creating rich superposition states that can encode intricate relationships within data. These quantum states can be processed by parameterized gate sequences, quantum neural networks, in which adjustable parameters guide the evolution of the system. Training such networks involves tuning parameters to minimize loss functions defined in terms of measurement outcomes, a process that parallels gradient-based optimization in classical deep learning. Quantum kernel methods offer another avenue for combining quantum and classical strengths. In these approaches, classical data points are embedded into quantum states via feature maps implemented by quantum circuits. The inner products of these states, quantum kernels, capture complex similarities that may be intractable for classical similarity measures. Once the kernel matrix is computed through quantum evaluations, classical algorithms perform classification or regression in this high-dimensional space. Quantum kernel estimation can, in principle, exploit non-classical correlations to distinguish data patterns that elude classical kernels, potentially improving generalization performance on certain datasets. Variational quantum algorithms form a powerful class of hybrid quantum classical methods essential to near-term quantum machine learning. In the variational paradigm, quantum circuits with adjustable parameters generate trial states. Classical optimizers iteratively update these parameters by evaluating cost functions measured on quantum hardware. This approach underlies quantum neural networks, quantum autoencoders, and variational classifiers. Quantum autoencoders compress quantum or classical data into reduced representations by training circuits to reproduce input states from smaller latent spaces. Variational classifiers learn decision boundaries by training parameterized circuits to maximize classification accuracy on labeled data. The hybrid structure leverages quantum circuits for expressive transformations while relying on mature classical optimizers for parameter updates. Generative modeling in the quantum domain explores how quantum circuits can learn to produce samples from complex distributions. Quantum generative adversarial networks, QANs, adapt the classical adversarial framework, pairing a quantum generator circuit with a classical or quantum discriminator. The generator aims to produce samples that mimic training data, while the discriminator learns to distinguish generated from real samples. Training proceeds through adversarial updates that refine both generator and discriminator. Quantum circuits may naturally sample from distributions that capture intricate correlations, potentially improving generative performance on tasks like anomaly detection, image synthesis, or molecular design. Optimization underpins many machine learning tasks, and quantum annealers offer a distinctive route to solving combinatorial optimization problems. By encoding optimization objectives into energy landscapes of quantum systems and exploiting quantum tunneling, quantum annealers can escape local minima more efficiently than classical heuristics. Hybrid quantum classical optimization loops use annealers for subproblems or initial candidate solutions, followed by classical refinement. Applications span portfolio optimization, scheduling, and feature selection, where discrete variables dominate. Training quantum machine learning models confronts challenges distinct from classical scenarios. Shot noise, statistical fluctuations from finite measurement samples, introduces stochasticity in cost evaluations. Parameter landscapes may exhibit barren plateaus, regions where gradients vanish, hindering effective optimization. Researchers explore tailored cost functions, initialization strategies, and alternative optimization methods, such as quantum natural gradient, which accounts for the geometry of quantum state space. Regularization techniques mitigate overfitting by including penalty terms or incorporating noise into training, leveraging quantum decoherence as a form of implicit regularization. The choice of data encoding critically influences quantum machine learning performance. Amplitude encoding packs data into amplitude values of quantum states, enabling exponential compression but requiring complex state preparation. Angle encoding maps features to rotation angles of single qubit gates, offering simplicity but linear scaling in qubit resources. More advanced schemes interleave encoding layers with entangling operations, creating feature-entangled representations that capture nonlinear relationships. Designing efficient, scalable encoding procedures remains an active research area, balancing circuit depth and expressive power. Benchmarking quantum machine learning algorithms demands careful experimental design. Synthetic datasets with known structures, such as Gaussian mixtures or XOR patterns, help assess the expressive capabilities of quantum models relative to classical baselines. Real-world datasets, from image recognition to financial time series, serve to test quantum models under practical constraints. Benchmark protocols measure classification accuracy, training convergence speed, and resource consumption, including circuit depth, qubit count, and measurement shots. Comparative studies reveal regimes where quantum approaches may offer speed-up or improved accuracy, guiding application selection and hardware development. Software frameworks accelerate quantum machine learning research by integrating quantum simulation, circuit construction, and classical optimization. Libraries provide ready-to-use routines for variational classifiers, kernel evaluation, and QGAN training, abstracting hardware-specific details and allowing algorithm designers to focus on model innovation. Cloud-based quantum platforms enable seamless switching between simulators and real devices, supporting cross-validation of results and rapid prototyping. Open-source communities collaborate on shared benchmarks, optimization strategies, and noise mitigation techniques, fostering transparency and reproducibility. Hardware considerations shape the feasibility of quantum machine learning applications. Superconducting qubit arrays excel at executing shallow, parameterized circuits with moderate coherence times, while photonic platforms offer natural integration of optical data channels and room temperature operation. Trapped ions deliver high-fidelity gates and robust coherence, but face limitations in qubit connectivity and gate speed. Each platform's characteristics influence algorithm design, from circuit depth constraints to noise resilience. Architectural co-design, where hardware and algorithm development proceed in tandem, optimizes performance by tailoring algorithms to platform-specific strengths and limitations. Quantum error mitigation techniques play an important role in near-term quantum machine learning. Methods like probabilistic error cancellation and zero-noise extrapolation, borrowed from broader quantum computing contexts, help reduce bias in cost evaluations, smoothing training landscapes, and improving model generalization. Pulse-level control and active error suppression strategies refine gate implementations, minimizing error accumulation during training loops. Researchers also explore noise-aware model architectures that exploit device error profiles to design circuits inherently robust to dominant noise sources. Interpretability and explainability in quantum machine learning present unique challenges. Quantum models often operate in high-dimensional Hilbert spaces, making it difficult to map learned patterns back to human understandable features. Techniques for visualizing quantum decision boundaries, extracting salient features, and quantifying feature importance are under development. Understanding quantum model behavior is essential for deploying machine learning in sensitive applications, such as healthcare diagnostics or autonomous systems. As hardware and algorithms mature, quantum machine learning may unlock breakthroughs in domains where classical methods struggle. Drug discovery pipelines could benefit from quantum-enhanced generative models for molecular design. Financial institutions may leverage quantum classifiers for anomaly detection in complex trading behavior. Large-scale optimization tasks in logistics and energy grid management might see accelerated solutions through quantum annealing and variational approaches. Quantum machine learning stands poised to augment or surpass classical AI capabilities in selected high-impact areas. However, realizing these benefits depends on overcoming scalability hurdles, mitigating noise, and establishing clear benchmarks for quantum advantage. Collaborative efforts between academia, industry, and government aim to coordinate research roadmaps, standardize evaluation criteria, and invest in training the next generation of quantum AI specialists. Education programs integrate quantum information science with machine learning curricula, preparing practitioners to navigate both theoretical and practical challenges. In summary, quantum machine learning unites the strengths of quantum processors with the methodologies of artificial intelligence, offering new computational paradigms and specialized tools for data-driven discovery. While current implementations explore limited-scale prototypes, the field's rapid evolution suggests that quantum-enhanced AI applications will play a pivotal role in the broader quantum information era. By refining models, optimizing hardware, and forging interdisciplinary collaborations, researchers will chart a path toward quantum machine learning systems that leveraged the quirks of quantum mechanics to solve problems beyond the scope of classical methods. Chapter 9. Quantum Metrology: Ultra-Precise Measurements Through Quantum Mechanics. Quantum metrology stands at the forefront of precision science, leveraging quantum phenomena to achieve measurement sensitivities unattainable by classical means. It underpins advanced technologies ranging from the most precise clocks ever built to the detectors that perceive ripples in space-time. By exploiting non-classical states and entangled resources, quantum metrology transcends classical noise limits, enabling researchers to probe physical quantities with unprecedented resolution. This chapter examines the principles, implementations, challenges, and applications of quantum metrology, illustrating how quantum mechanics reshapes our approach to measurement. The foundation of quantum metrology lies in overcoming fundamental limits imposed by classical strategies. In traditional measurement, uncertainty arises from technical noise and statistical fluctuations, constraining the attainable precision. Quantum metrology introduces specialized quantum states that suppress noise contributions or amplify signal responses. Superposition and entanglement permit collective behavior of multiple particles or photons, concentrating measurement information into correlations that yield enhanced sensitivity. By carefully engineering these correlations, quantum sensors operate near ultimate precision bounds dictated by quantum theory. One of the earliest and most profound quantum-enhanced measurement techniques involves the use of squeezed states of light. In these states, quantum fluctuations in one observable are reduced below classical levels, compensated by increased uncertainty in the conjugate observable. When applied to interferometric measurements, squeezed light reduces phase noise, improving the detection of minute changes in optical path length. Gravitational wave observatories have embraced this innovation, injecting squeezed light into interferometers to boost their ability to sense tiny distortions of space-time caused by distant cosmic events. The successful integration of squeezing into large-scale experiments validates the promise of quantum metrology in pushing observational frontiers. Beyond photons, ensembles of atoms or ions also serve as powerful quantum sensors. By preparing large collections of particles in entangled spin-squeezed states, researchers create atomic ensembles with reduced uncertainty in collective spin projections. Such ensembles improve the stability and accuracy of atomic clocks, which measure time by locking laser frequencies to atomic transition frequencies. Quantum-enhanced clocks exhibit lower time fluctuations, advancing the definition of the second and enabling timekeeping with fractional uncertainties approaching parts in quintillions. The resulting optical clocks surpass microwave-based standards, opening pathways to more accurate global positioning systems and tests of fundamental physics. Atom interferometry extends the concept of wave-particle duality to matter waves, using coherence splitting and recombination of atomic wave packets to measure accelerations, rotations, and gravitational gradients. Quantum correlations among atoms within an interferometer enhance sensitivity to inertial forces, enabling ultra-precise measurements of acceleration and rotation rates. These quantum-enhanced inertial sensors hold promise for navigation in GPS-denied environments, monitoring seismic activity by detecting ground vibrations, and mapping variations in the Earth's gravitational field for geophysical surveys. Key to quantum metrology's success is the concept of entanglement-enhanced measurements, where entangled states of many particles yield precision scaling beyond classical limits. In a classical ensemble, measurement uncertainty decreases with the square root of particle number. In contrast, entangled probes can, in principle, reduce uncertainty inversely proportional to particle number, approaching the Heisenberg limit. Achieving this advantage requires generating and maintaining multipartite entanglement under realistic conditions, as well as devising readout strategies that extract collective information without destroying fragile correlations. Quantum sensors also exploit coherence in solid-state systems. Defect centers in diamond, such as nitrogen vacancy centers, possess spin states that can be initialized and read out optically. These spin states interact sensitively with magnetic and electric fields, temperature, and strain in their environment. By employing coherent control techniques and entangling multiple defect centers, researchers create nanoscale sensors capable of detecting single-spin signals from nearby molecules or mapping magnetic fields with nanometer resolution. Such quantum probes have applications in materials science, biology, and fundamental studies of condensed matter phenomena. Realizing the full potential of quantum metrology demands sophisticated control over quantum states. High-fidelity preparation and readout, isolation from environmental noise, and precise manipulation via tailored pulses are essential. Techniques such as dynamical decoupling prolong coherence times by applying sequences of control pulses that average out noise. Feedback stabilization employs real-time measurement outcomes to adjust system parameters, compensating for drift and maintaining optimal operating conditions. Advanced calibration procedures ensure that quantum enhancements translate into tangible performance gains in applied settings. Practical quantum metrology systems must contend with loss, decoherence, and imperfect operations. These imperfections degrade the non-classical correlations that underpin enhanced sensitivity. To mitigate these effects, error mitigation techniques borrowed from quantum computing adapt to metrology tasks. For instance, error extrapolation measurements estimate ideal signal levels by combining data collected under varied noise strengths. Bayesian estimation frameworks incorporate prior knowledge and adapt measurement strategies dynamically, maximizing information gain per quantum resource used. The impact of quantum metrology extends across scientific and technological domains. In fundamental physics, improved clocks and interferometers test variation of constants, search for dark matter signatures, and explore gravitational redshift with unprecedented accuracy. Networks of synchronized quantum clocks distributed over large distances enable new geodetic measurements, mapping subtle variations in Earth's gravitational potential that reflect changes in mass distribution, such as groundwater levels or tectonic shifts. Quantum magnetometers detect minute magnetic anomalies, aiding in mineral exploration and archaeological surveying. In industry, quantum-enhanced sensors optimize semiconductor fabrication by monitoring process parameters at nanoscale precision. Healthcare applications emerge as quantum sensors detect biomagnetic signals from neuronal activity or cardiac currents with unmatched sensitivity, paving the way for non-invasive diagnostics. Chemical process industries benefit from ultra-precise temperature and pressure measurements, improving yield and safety. Quantum metrology thus catalyzes innovation across sectors, translating fundamental advances into practical tools. Scaling quantum metrology platforms to commercial viability involves overcoming engineering and integration challenges. Packaging quantum sensors into robust, field-deployable units requires miniaturization of control electronics, management of thermal environments, and mitigation of vibrations. Developing turnkey systems demands standard interfaces for classical communication and data processing. Collaborations between quantum scientists, engineers, and application experts are vital to tailor quantum sensors to specific use cases, balancing performance, cost, and reliability. Interfacing quantum sensors with classical networks unlocks new capabilities in distributed sensing. By entangling sensors at remote locations, researchers create sensor networks with correlated measurement outcomes, enhancing precision in global array measurements. Distributed quantum sensing schemes explore how entanglement among multiple sensors yields collective sensitivity improvements that surpass individual capabilities. Such networks could revolutionize Earth observation, environmental monitoring, and collaborative scientific experiments spanning large distances. Looking forward, the future of quantum metrology encompasses integration with other quantum technologies. Quantum communication networks will distribute entanglement among sensors and clocks, synchronizing measurement standards over global scales. Quantum computers could optimize sensor configurations, analyze complex measurement data, and simulate sensor-environment interactions to refine designs. Hybrid quantum systems combining diverse platforms, atoms, photons, spins, offer multifunctional sensing modalities capable of probing multiple physical quantities simultaneously with quantum-enhanced accuracy. Advancements in materials and nanofabrication will enable novel sensor architectures. Photonic crystal structures can confine light at sub-wavelength scales, enhancing light-matter interactions and boosting sensitivity in optical sensors. Engineered spin defects in emerging materials promise new platforms for magnetic and electric field sensing at the atomic scale. Integrated quantum photonic circuits will combine state generation, manipulation, and detection on chip, paving the way for scalable quantum sensor arrays with high throughput. Achieving sustainable progress in quantum metrology requires concerted efforts in education, workforce development, and standardization. Training programs must integrate quantum theory with practical engineering skills to cultivate professionals capable of designing, building, and deploying advanced quantum sensors. Standards bodies will establish calibration protocols, performance benchmarks, and interoperability guidelines that ensure consistency across devices and platforms, fostering confidence in quantum measurements for critical applications. In conclusion, quantum metrology transforms our ability to measure the world by harnessing quantum coherence and entanglement to achieve precision beyond classical constraints. From redefining fundamental constants to enabling next-generation navigation and sensing technologies, quantum-enhanced measurements open new vistas for science and industry. As quantum metrology evolves, its integration with computing, communication, and sensing infrastructures will usher in an era where the precision of our measurements matches the unprecedented capabilities of quantum theory, driving discovery and innovation in the quantum age. Chapter 10: The Quantum Future: How Quantum Information Will Transform Society. The ongoing evolution of quantum information science heralds a profound transformation of society's technological foundations, reshaping industries, redefining scientific inquiry, and reframing human interaction with information. While the initial focus has been on isolated demonstrations and proof-of-concept prototypes, the coming decades will witness quantum technologies maturing into reliable, scalable solutions. As quantum processors, networks, and sensors move from laboratory curiosities to integral components of infrastructure, they will unlock capabilities far beyond the reach of classical systems. This chapter explores the multifaceted impact of quantum information, from near-term applications to long-range visions, and addresses the technical, economic, and societal challenges that will guide quantum innovations toward broad adoption. In the near term, quantum computing will complement classical high-performance computing by accelerating specialized workloads. Simulation of molecular systems will refine drug design and materials discovery, while optimization tasks in logistics, energy management, and financial modeling will benefit from quantum-enhanced algorithms. Industries will deploy hybrid quantum classical systems, routing subroutines to quantum coprocessors for critical tasks, while retaining classical architectures for general processing. Cloud-based quantum access models will democratize technology, allowing startups and research labs to experiment without owning hardware. Early adopters in sectors such as pharmaceuticals and chemicals will gain competitive advantages by reducing R&D timelines and uncovering novel solutions through predictive quantum simulations. Cryptography will undergo a twofold evolution driven by quantum advances. First, existing public key infrastructures will transition to quantum-resistant algorithms, ensuring that encrypted data remains secure against both classical and quantum attacks. Second, quantum key distribution and device-independent protocols will supplement classical encryption, providing information-theoretic security for the most sensitive communication channels. Governments and large enterprises will establish quantum-secure networks for defense, finance, and critical infrastructure coordination. International collaboration on standards and certification processes will be essential to ensuring interoperability and trust, preventing fragmentation as countries and organizations define divergent security frameworks. Quantum sensing and metrology will transition from specialized experiments to integrated industrial solutions. Quantum-enhanced sensors, ranging from atomic clocks that synchronize global positioning systems to magnetometers that map brain activity, will be embedded in medical diagnostics, navigation arrays, and environmental monitoring systems. The ubiquitous deployment of these sensors will foster new applications. Real-time health monitoring devices that detect disease biomarkers at early stages, infrastructure monitoring tools that predict structural failures, and climate observation networks that measure atmospheric variables with unparalleled precision. Integration with Internet of Things platforms will create dense sensor grids, feeding data into analytics engines powered by quantum-enhanced AI. Quantum networks represent the backbone of a future information infrastructure, connecting quantum computers, sensors, and secure communication links across local, national, and global scales. In metropolitan areas, fiber-based quantum metropolitan area networks will link research centers, data centers, and critical facilities. Satellite quantum links will extend these networks to remote regions, enabling entanglement-based, secure communication between continents. Over time, a layered architecture will emerge, combining quantum repeater nodes, optical ground stations, and network orchestration tools. Standardized protocol stacks will govern quantum routing, resource allocation, and network management, mirroring classical internet designs, but enriched with quantum-specific control channels. The convergence of quantum technologies with artificial intelligence and classical computing architectures will create synergistic ecosystems. Quantum-enhanced machine learning models, trained on hybrid hardware, will tackle complex pattern recognition tasks in fields such as genomics, astrophysics, and financial forecasting. AI agents will optimize the configuration and calibration of quantum hardware, dynamically balancing error mitigation, resource allocation, and algorithm parameters. Conversely, quantum processors will empower advanced AI applications, enabling exploration of high-dimensional optimization landscapes, accelerating reinforcement learning for robotics, and facilitating generative design in engineering. Education and workforce development will be pivotal in preparing society for the quantum revolution. Curricula at all academic levels will incorporate quantum information principles alongside computational thinking and data science. Interdisciplinary programs will train professionals skilled in quantum hardware engineering, algorithm design, network architecture, and ethical policy. Massive open online courses, hands-on laboratories, and quantum cloud access will expand learning opportunities globally, fostering inclusive participation. Apprenticeship models and industry research partnerships will accelerate experiential learning, ensuring that graduates possess practical skills for deploying and managing quantum systems in real-world environments. Ethical, legal, and societal considerations must accompany technological progress. The power of quantum computation to break existing cryptography underscores the need for responsible transition strategies that protect data privacy and prevent asymmetric vulnerabilities. Quantum sensing capabilities, such as the ability to penetrate obfuscating materials or monitor physiological signals remotely, raise questions about surveillance, consent, and personal autonomy. Policymakers, ethicists, and technologists must engage in proactive dialogue to establish guidelines for the acceptable use of quantum technologies, balancing innovation with individual rights, public safety, and global equity. Economically, quantum information will spawn new markets and disrupt existing ones. Hardware manufacturing industries will expand from niche cryogenics and photonics to mass production of qubit chips, integrated photonic circuits, and hybrid electronic quantum modules. Software ecosystems will flourish as quantum algorithm marketplaces emerge, offering domain-specific algorithm packs and optimization services. Consulting and professional services will grow to support quantum deployment, maintenance, and integration. Established technology companies and startups alike will vie for leadership in quantum ecosystems, driving competition and collaboration that accelerate progress. Environmental and sustainability goals will shape quantum development pathways. The energy demands of large-scale quantum data centers will necessitate green infrastructure designs, embracing renewable power sources and energy-efficient cooling techniques. Research into room temperature quantum devices and photonic platforms will reduce reliance on resource-intensive cryogenic systems. Quantum simulations will aid climate modeling and the design of low-carbon technologies, while quantum optimization will streamline resource distribution in energy grids and supply chains, minimizing waste and emissions. International cooperation will underpin the successful rollout of quantum infrastructure. Multilateral frameworks will coordinate spectrum allocation for free space quantum links, harmonize standards for hardware interoperability, and facilitate cross-border research collaborations. Quantum diplomacy initiatives may arise to manage dual-use concerns, ensuring that quantum capabilities serve peaceful and equitable purposes. Developing nations will require capacity-building support to participate in the quantum economy, preventing a technology gap that mirrors existing digital divides. Looking toward long-term horizons, quantum technologies may converge with emerging fields, such as synthetic biology, nanotechnology, and brain-computer interfaces, to enable breakthroughs beyond current imagination. Quantum simulations could model complex biomolecular networks, informing the engineering of novel life forms or personalized therapeutics. Quantum sensors integrated into wearable devices could provide continuous health and environmental feedback. Brain-computer quantum interfaces might eventually explore the quantum aspects of neural processing, although such prospects remain speculative and demand rigorous ethical scrutiny. The timeline for quantum integration spans multiple phases. In the coming 5 years, expect broader access to noisy quantum processors and sensor prototypes, along with maturing standards for quantum-safe cryptography. At the decade mark, mid-scale quantum computers with error mitigation and early error correction will tackle industrially relevant problems, while pilot quantum network segments interconnect research hubs and metropolitan areas. By mid-century, resilient fault-tolerant quantum machines and global quantum networks will underpin critical infrastructures, scientific research, and everyday applications, transforming how we compute, communicate, and measure. Realizing this vision will require persistent investment, cross-disciplinary collaboration, and adaptive policy frameworks that evolve alongside technological advances. As quantum devices transition from the laboratory to commercial viability, partnerships among academia, industry, and government will drive innovation, de-risk adoption, and ensure that quantum technologies deliver maximum public benefit. Navigating challenges, technical, social, economic, and ethical, will define the character of the quantum era, demanding foresight, flexibility, and a shared commitment to harnessing quantum potential responsibly. In summary, the quantum future offers a landscape of extraordinary opportunities and complex challenges. By integrating quantum computation, communication, sensing, and networking into the fabric of society, we stand on the cusp of a revolution as significant as the advent of electricity or the digital computer. Embracing this transformation with deliberate stewardship and inclusive governance will unlock the promise of quantum information, propelling human progress into an era of discovery and innovation guided by the fundamental principles of quantum mechanics. Thanks for sticking with me, friend. I hope you enjoyed uncovering how quantum information is poised to transform our world. If you're curious for more, be sure to check out the next video in this series. There's so much more quantum wonder to explore. Sleep well, and sweet dreams among the stars.